Hello students, welcome back. We just completed section 1, random variable. We discussed what it meant and went through some examples. All those examples we had from section 1 are all about discrete random variables, remember? Now, let us consider something called the probability distribution of those discrete random variables. Here we go. Given discrete random variable x, the probability distribution of that discrete random variable consists of two functions. Number one, the probability mass function defined like this, and number two, cumulative distribution function defined like that. Put these two functions together, that is PMF, the probability mass function, and CDF, the cumulative distribution function. Put these two functions together and form a single entity, and I'm going to call it the probability distribution of the given random variable capital X. And that's my definition. Now, what is this probability mass function and what is this cumulative distribution function? And we're going to come back and discuss these in a moment. For now, let's be satisfied with some terminologies. You see, this expression is a well-defined expression. This real function, p of x, where small x can be any real number, is defined as the probability that this random variable, capital X, is taking this small x value. Whereas in this case, small x is any real number, where this is the probability that the random variable capital X is taking a value of small x or less. So here we have equality, precise equality. Here we have inequality. Now, which is easier, by the way, equations or inequalities? You must have done those kind of things in intermediate algebra or and so on and so forth. But what is your experience? Which is easier? Solving an equation is easier than dealing with inequalities, of course. And it's going to be like that too. PMF is not going to be too difficult. CDF, on the other hand, will be a bit more challenging. Okay, we took care of these terminologies. Now let's go ahead and discuss what they mean, but one step at a time. We're going to talk about the probability mass function first, and then we're going to go over to the cumulative distribution function in a separate video. Okay, let's go to PMF, probability mass function, to run example problem. Okay, here we go. The same example. Same urn with same colored balls. 5 red, 3 green, and 2 blue balls. So that we have this sample space. The same example problem that we have been working on since week 4, I think. All right. Now, let's assign some numbers. Instead of RGB, we assign 0, 2, and 3 respectively, and nothing else. Now, the same game, we can play with some fees. So each time you play that game, you have to pay $1.50. Then the net is red minus 1.5, green positive 0.5, blue positive 1.5, like that. And this game Z is unrelated. In this case, red and green are the same, so there's no reason to distinguish those. There are only two possible outcomes. Now let's name those probability mass functions as small f, small g, and small h. By the way, it is traditional that we use lower cases for the probability mass functions and the capital for cumulative distribution function. You see, for cumulative distribution function, we use capital F, capital G, capital H. For the probability mass functions, we use lower cases. Okay, now let's go into part A. What is the structure here? Well, this is the first time you're going to deal with this. You're dealing with this probability mass function, so I better show you the answer. There, this kind of thing is called the probability mass function. We have only three possible values, RGB, 0, 2, 3. Otherwise impossible. So the probability of this random variable capital X taking 0 is the same as getting a red ball, so that's 5/10. And for value 2, that's the same as green ball, so 3/10. And for 3, that's 2/10. Now otherwise, all impossible, so probability is all 0. So you see, this X value can be anything, any real number. What if this X value is 2.13? Well, it falls here. So that probability is 0. So only for three possible X values, we have non-trivial probability values, otherwise all 0. These are called probability mass functions. You can express it like this, which I prefer, but some people do it like this. Capital X as the random variable as taking 0, 2, 3, or otherwise, and the probability, capital P of capital X, 5/10, 3/10, 2/10, and of course 0 like this. Now many people skip this part, otherwise 0 because it goes without saying. Me personally, I always goes in. Now one way to do this is to use this horizontal tabular form. Another way to do that is to use this vertical tabular form. X values are 0, 2, 3, otherwise, and the probabilities are 5/10, 3/10, 2/10, and otherwise 0. Same as this, just expressed differently in vertical tabular form. Or you can label as P of X of probability and capital X for the random variable. You can do it like that. Me personally, I like to do it small, but there are some problems that are written like this as well. I found those from my math lab too. Another way to explain the same thing is to use the piecewise defined function expression. Oh, I should not have closed these cells. From here, this vertical tabular expression, suppose that you don't have rulers and everything, so it's cumbersome to draw all those boxes. F of X values can be 5/10, 3/10, and 2/10. I simplified, but on second thought, probably it's better without simplification. And they correspond to X values of 0, 2, 3, respectively. And of course, there's a color coding to help you understand. They correspond to RGB from the original sample space. And of course, the probability is 0 otherwise. And curiously enough, if you use this piecewise defined function form, then nobody ever skips this otherwise 0. I've never seen anybody skipping this. In tabular form, I've seen many people skipping this part, otherwise 0, in many books. But curiously here, I've never seen anyone skipping this. Anyway, you have all different expressions here. Now, if you're really comfortable with algebra, then maybe you would like it. And I'm afraid all the teachers are professional mathematicians, and they became mathematicians because they like these kind of things, algebra especially. So they tend to do these a lot. I'll do only to a certain degree, not too much. But even if I take this path, you should be able to understand it and translate it into the tabular form. It's not going to be too bad. Just pick up a ruler and pencil and then draw a table, and that's it. All right, so what are the probability mass functions? Small x value will be those allowed outcomes, allowed payoffs, and then otherwise we have probability of 0. Now, let me show you the graph expression of the same thing. If you have a function, a real valued function, you can always graph it. For x equal to 0, we have the probability of 5/10, colored in red. x value is 2, then you have probability of 3/10. X value is 3, then you have probability of 2/10. Otherwise, all 0. That's the graph. You have a dot plot. And this is typical. Some people prefer to draw rectangles over here, like this. So do kind of like this. Like this, and call it probability histogram. And that's quite common too, as a matter of fact. And our textbook author does not really emphasize probability histograms, but and some other textbooks do. And if you use these probability histograms with these rectangles, make sure that you get non-overlapping rectangles with the same width. If you have different widths, then it can deceive your eyes. And also, if they overlap, then it creates a huge mess. So never do that. It should be non-overlapping rectangles with the same width. Of course, it is best if you just avoid all these. If you just go back to dot plot, then you don't really have to worry about those rules about those rectangles. Now, one final comment here. And let's open, no, not these. That's enough. Let's open these. If you sum up all these probabilities, what do you get? Always you get 1. So basically, if you sum up all those if you sum up these, so in this case 0, and in this case 2, and in this case 3 for RGB, always you get the total probability of 1. And of course, if you have more complicated table for a different random variable, if you have 17 of these, then you have to add up 17 of those. Always they will have to end up with precisely 1 because you're adding up everything, the total probability. Now, how about the other problems? Well, I'll give you some time to work on the second problem. It's going to be pretty much the same. 3 possible values, negative 1.5, 0.5, 1.5, otherwise, and then get appropriate probabilities associated to this model. RGB, 5/10, 3/10, 2/10. In the end, you're going to get these. Clear? Vertical tabular form, piecewise function form, and then finally, if you graph it, you're going to get these dot plots. Negative 1.5, 0.5, 1.5, those are x values, and heights are the probabilities. Heights all add up to 1 as before. How about the third case? Well, again, I'll leave that as an exercise for you. It's going to be even simpler. With 2 possible non-trivial probabilities. Dot plots are simpler. All right, so much for the probability mass functions. We're going to discuss the cumulative distribution functions in separate videos.